Okay, and we're now at the third session, and I welcome on stage Daniel Situnayake, founding tinyML engineer at Edge Impulse, building data-centric AI tooling for embedded engineers. Thank you, Daniel.
Awesome. Well, hopefully you can hear me. It sounds good. So it's so nice to be here. It's so nice to see some old friends and make loads of new ones and be back here in person. It seems like it's only been a short time since the first tinyML summit. But in that space of time, there's been so much that's happened, and I'm really excited to share my little corner of that with you. So as Alessandro said, I lead the ML team at Edge Impulse. Previously, I worked on TensorFlow Lite for microcontrollers at Google, which is how I met a bunch of you. I wrote the tinyML book with Pete Warden, and currently working on another one called AI at the Edge with Jenny Plunkett, which is going to come out soon. So Edge Impulse is basically a product that gives you an engineering toolkit for embedded engineers to work with machine learning on device. We kind of reimagined the way MLOps works specifically for embedded. And we do end-to-end integration with a bunch of different tools. It kind of looks like this. I'm not going to go into every little detail, but we do stuff starting at the very beginning with capturing data from devices, training models, massaging data sets, working with signal processing, and then getting those models running on devices at the end. We've got a ton of users, a ton of developers building loads of amazing projects, including some big enterprise customers. So we've got a lot of traction, and we're really kind of understanding the way people need to build with Edge AI. And that's what kind of leads me to this next slide, which these are my top 3 things which I think are most important to the developer experience for embedded machine learning. Those are feedback loops, data-centric AI, and rapid development. And so in this talk, I'm just going to go through what these mean and why they're important in the things that we do, and talk about some of the technologies that support our product in these areas. At the end, I'm going to share a little bit of my kind of predictions for where the tooling is going to go generally over the next few years. So first of all, feedback loops. I think feedback loops are at the heart of the machine learning workflow. I think this is the bread and butter of what we do when we're trying to get good performance from any kind of AI system. It's all about continuous improvement. And if you think about the basic Edge ML workflow, everyone's got a variant of this slide in their deck. You've got data being collected, creating a model, testing it, deploying it, and then running it in the real world, seeing how it works. But if you think about this, this is one big feedback loop. But contained within this are a ton of others. For example, between collecting data and designing a model, there is feedback. The type of data impacts the type of model you're training. The results of training that model sends you out into the field to collect more data. And in fact, there are feedback loops between that data collection part and every other stage in the process, if you think about it, going through testing, deployment, field testing. And actually, every single node of this graph is connected to every other. There's not just one big feedback loop, but we have all these tiny feedback loops throughout every part of the process, and each one of those is vital. And the real goal is that we want to have all these feedback loops be as tight as possible, because if we can iterate quickly and make changes in one area and see how they impact another, we can rapidly improve things. But the problem is, in reality, that feedback loop involves a lot of little steps. So we might design a model architecture that we think is going to work, but then we've got to code it, train it, optimize it, integrate it into an application, deploy it to device, and on embedded, this gets even harder. So the real challenge is, how do we shrink all this complexity back down into a really simple, tight feedback loop? So here are some of the things we've done. So one of those is reducing data requirements. The less data you need to get started or to get to a production-ready state, the better. So one example of this in Edge Impulse is we have built a few-shot keyword spotting system, which allows you to train a keyword spotting model, which you can get up and running and have reasonable testing-worthy performance with 5 samples of a keyword. There are tons of ways to do this in other domains, and leaning on this is really important. A second thing is reducing training time. So if it takes ages to train or retrain a model, you're going to struggle to tighten feedback loops. So we have this really awesome cloud infrastructure that we've built so that when you go to train a model, you just click a button, it goes into our Kubernetes-based job system, we find the right hardware to run it, and we train a model as quickly as possible, and you don't have to mess around provisioning machines and all this extra stuff that can get in the way of getting your results. We also have the Eon Tuner, and this is a feature based around the idea that a lot of the time you spend on model development is spent fine-tuning, often by hand and in a fairly arbitrary way, the signal processing and machine learning parameters and hyperparameters. So we're looking at things like the architecture of a network or the number of filters in your FFT. And really you need to take a look at that across the board and how it impacts performance on your specific target device. So if we can take that part off your hands and give you a good, easy baseline of decent performance by just clicking a button and analyzing a particular data set, that tightens a feedback loop and gets you into testing more quickly. So speaking of testing, once you've got a model, it's not enough to know that it has good performance on a holdout data set. Really, we want to test it in the real world. But there's a lot of difficulty and complexity between getting a model from your development space into the field. And what we try to do there to narrow the feedback loop is to bring some of the field into the software. So our performance calibration tool basically allows you to upload big, long samples of real-world data that either you label or we'll help you label. And then we'll run your signal processing model across that and try to understand the performance in the real world given a specific post-processing algorithm. And that algorithm can be tuned in the performance calibration process. We use a genetic algorithm to tune the hyperparameters or the parameters of the post-processing algorithm to give you a Pareto front of false accepts versus false rejects. So you can pick the right thing for your application. And typically, this was something that everyone's been doing by deploying to a device and getting basically qualitative data back of how people think it's performing. So by moving this into the engineering process and quantifying it, we get some big wins. So the second big topic is data-centric AI, and the idea that you really need great data to have great performance. It's the inverse is garbage in, garbage out. Traditional AI focuses on modeling. We're sort of saying, how do we train the best model for this particular data set? But with data-centric AI, we move the focus up a little bit. We're focused on the data set instead of just the model. And this is really asking, how do we create the best data set to solve this problem? And the reason this is awesome is because we're focusing on the first node in our chain, and it has a knock-on effect downstream into every other section. So if you do a good job here, everything else becomes much easier. So one of the things we do here, in the real world, everybody's data is messy, it's in lots of different places, it's in scruffy formats that don't match what we're going to be seeing on device in the real world. And there are a lot of different tools for working with data. So we've built systems that allow you, using Docker, to define transformations which will be applied to data that comes from all sorts of different sources to feed into your projects. And then we can run those in the cloud without you having to know anything about cloud compute. The most data that we have is unlabeled, right? It's really easy to collect unlabeled data. The problem is labels are really, really important for most of the ML that we do these days. So building tooling that assists the labeling process is really, really helpful. So letting you pull in huge amounts of unlabeled data that you may already have or that you can easily go out and collect, and then use machine learning to assist labeling models, whether it's through tracking objects frame to frame that you're manually labeling, or using another model in the loop, including an early version of your own model to help label. Dataset exploration is really important too, so getting an at-a-glance understanding of your feature space and how it impacts the model that you're building. So we've built a load of tools based around dimensionality reduction that allow you to project your entire data set into a low-dimensional space that you can explore and analyze to see at a glance whether you have outliers or mislabeled samples, or whether there are clusters in your data that might be indicative of differences in your collection methodology that you might not be aware of. This is super effective for processed signals, so things that have gone through feature engineering. But if we're looking at high dimensionality data, we need to dig into the specific modalities of that data in order to understand it better. So for example, in this image here, we're showing a set of features generated by a keyword spotting feature extractor that allows us to explode a data set out into this two-dimensional space. And it's quite small, but you can just about see that there are lots of outliers or mislabeled samples dotted around that we can easily pick out and relabel. So for data, really, we want to have this data feedback loop that's kind of separate from the other one, or it's a subcomponent of it, where we're collecting data, visualize it, and identifying any outliers. And the really cool thing comes when we can loop in models to that loop and use those to help augment our ability to work with data. And the other big part of it is feature engineering, which is another one of those things where we tend to be fairly arbitrary. We pick some values that we read in a paper or that have worked well for us before, and we kind of don't have much insight into whether they're the best or not. But by providing interactive tooling, which we do using a service-based architecture so that you can run DSP on individual samples from a data set, you can then toy with different values in your feature engineering and start to understand how they impact what the data looks like. We can also measure the importance of individual features, so we can avoid using features we don't need to. So this adds another feedback loop of feature engineering, which is just as important a part of the data-centric AI. But the last thing I wanted to talk about was rapid development. So this is around how do we do hardware at the speed we're accustomed to doing software at. And so this starts with data ingestion. So data ingestion is different throughout the flow. At the beginning, we want to capture a few samples from a device, train a basic prototype of a model, see if it works, and then we can invest more money in collecting large amounts of data, uploading bulk data, and then at the end of a project, we want to collect data from the field and feed it back into the system. So to do that, we've designed a low overhead data format that we can use for on-device use. We've built data forwarders that you can use in the lab to get data from the various places you need. And we've also got systems for ingesting data from cloud services. The Eon tuners are really important for rapid development too, because it lets you establish a really quick baseline. Essentially, you come in, grab a small data set, click a button, and you've got a baseline for performance, which is what you can measure all of your future optimizations against. And that's really important. And to allow that to work quickly, we use a distributed architecture where we've got reusable cloud workers that essentially reduce the startup cost of spinning up new jobs. And that allows us to quickly run a big exploration of the space, try loads of different DSP and model variants, and then you can pick one and customize it and have a baseline to work against. All of our systems use containerization heavily, so this lets you also plug in your own models. If you have a complex training loop with a lot of crazy dependencies, you can describe that in a Docker file and plug it into Edge Impulse, and it will drop into the system in a way that can make use of all of these upstream and downstream features too. We also have awesome firmware that makes development really easy. So at the front end, it lets you collect data super easily from a device. And on the testing end, you can deploy your model directly to a pre-built firmware, so you can try it out without having to write any code. So we're closing the loop on both of those ends. We also have this super lightweight SDK, which is generally how you'll integrate with real devices. So it's a C++ SDK. We wanted to pick a lowest common denominator that works across the majority of devices that people are using in the field. And for deployment, we can also customize this. So if you wanted to do some micro TVM deployment, for example, you can just describe that in a Docker container and run it automatically. So very quickly, I want to give a little glimpse of my idea of the next 5 years of Edge AI tooling. So you may disagree or have other thoughts. But I think it divides into these three pieces. First of all, hardware and software are going to get closer together. So we're going to see automatic tailoring of algorithms for hardware. We're already trying to do this with things like Eon Tuner and micro TVM. But then the next step is, how do we make it easier for someone who knows a lot about the software side to select and configure hardware appropriately, so that it's not just people who are working in the embedded space who can build here, but it's people who understand the ML side but need help selecting targets. And the third part is, what if we can go and directly design hardware based on models? So there's some really interesting stuff that's coming out around that. The next step is closing the loop with deployed devices. So I think being able to understand on device whether you're going out of distribution or if there's drift in your data is going to be really key to monitoring in the field, because we don't get to close the loop and bring back loads of data because there's usually not much bandwidth. Secondly, we want to have deep insights into model performance in the field. So how can we understand whether a model is continuing to work effectively once it's been deployed? And the third thing is, how do we split workloads and manage workloads across heterogeneous compute, whether that's on a device with multiple processors or as a mixture of cloud and edge workloads. And the third part is making better use of our precious resources. So like I said, that's tools for working with unlabeled data, making sure that we can make the most of every scrap of data that we've got. And then building edge-specific tools for human-in-the-loop learning. So what if we've got data that's in a tricky modality for a human to understand, so time series from arbitrary sensors, but we want to involve a human in the loop to label strategic samples so that we can basically expand our data set? How do we do that with data types that are difficult for us to interpret? And finally, collaborative tooling for community development so that we can have the same kind of energy that comes from the open source community around open source software and source code applied to models and signal processing. So thank you very much for the opportunity to talk today. I'd like to say that we're hiring lots of people, so if you're interested in any of these exciting topics that we're exploring, please don't hesitate to reach out. And we have a QR code here that will dump you right into Edge Impulse, and you can try out that few-shot keyword spotting model in about 5 minutes. So yeah, let me know if you have any questions, but thank you very much for being here.
Thank you, Dan. Thank you for the great presentation.
And we are very thankful for our sponsors. The premier sponsor this year is Edge Impulse. And then executive sponsors are ARM, DeepLight, Qualcomm, and Syntiant. Platinum sponsor, Analog Devices, BrainChip, Infineon, Clickertech, Latent AI, NXP, Reality AI, Renaissance, Sony Semiconductor, and Synaptics. Really very diverse company, great companies who are really driving tinyML forward. And gold sponsors for the Hub, Micro AI, Prophecy, Seed Studio, SenseML, ST Microelectronics, SynSense, XMOS. And we have a list of civil sponsors: Avion Devices, Aspinity, Seva, EMSA, Greenwave Technologies, Grovity, Hymix, HOTG, Imagimob, Itemis, Lattice, Nota, OmniML, PixArt, Plumerai, Kixo, Rachner, Rixen, SAP, StreamAnalyze, Texil, and Google. So we are very thankful for their support, and more importantly, for them being part of this community and driving it forward.